Alright, good morning class. Magandang umaga sa ating lahat. I hope everyone is as excited as I am with our lesson for today, which is on oxidation reduction reactions. Okay, redox reactions are oxidation reduction chemical reactions in which the reactants undergo a change in their oxidation states. This is due to the transfer of electrons. Now, the term redox is simply a short form of reduction oxidation. Okay, so redox is a short form of reduction oxidation. Now, all redox reactions can be broken down into two different processes: a reduction process and an oxidation process, which occur simultaneously. That means a reduction cannot proceed without an oxidation. So they go hand in hand. Now, the substance getting reduced. So what is a substance getting reduced? Meaning there is a decrease in the oxidation state. Okay, so the substance getting reduced is the oxidizing agent. Okay, so a reduction takes place and then that substance is the oxidizing agent. While a substance that is getting oxidized, meaning there is an increase in the oxidation state, is the reducing agent because an oxidation takes place. Okay, so if oxidation takes place, there is an increase in the oxidation state, then the substance is the reducing agent, and vice versa. Alright, so I have here a simple diagram of a redox reaction. So you notice that we have two substances, A and B. Notice that substance A has an initial oxidation state of 0, and after losing one electron, now has a charge of positive 1. So there is an increase in the oxidation state from 0 to positive, and therefore, we know that this is because of substance A losing an electron, and then oxidation takes place. On the other hand, substance B from 0 to negative gained an electron, and thus there is a decrease in the oxidation state, and therefore there is a reduction. So substance B decreased in oxidation state, so reduction takes place, and therefore substance B is the oxidizing agent. Whereas substance A, where oxidation takes place and there is an increase in the oxidation state, is the reducing agent. Okay, so this is what I said. So let me show you an example of a half reaction between hydrogen and fluorine. No? So it is imperative that the half reactions are balanced. Okay, so the number of electrons on the left side and on the right side must be balanced. So here, for our oxidation reaction, notice that hydrogen initially is 0. After losing electrons, it becomes positive. Since there are two atoms of hydrogen, so we need to affix 2 here so that the number of electrons lost, 2 electrons, would be balanced by these 2 hydrogen positive. Similarly, the reduction half reaction, fluorine is 0, it became negative, so there is a decrease in the oxidation state of fluorine. Why? Because fluorine gained 2 electrons in the process. Okay, so if you combine the two, then these 2 electrons on the right side of the equation will be cancelled out by these 2 electrons on the left side of the reaction. Okay, and then you will have finally 2H positive, 2H positive combining with 2F negative to form 2 moles of hydrogen fluoride. So we have another example, this time using this method for balancing. Okay, so the first thing that you need to do is to be able to identify the oxidation state. Now, where do we get the oxidation state? The oxidation states are the number, no, are the superscripts. So we have your 0, 0, positive 1, and negative 1. So you can get these numbers or the oxidation state from a table, no? Table of oxidation states or oxidation numbers. Okay, so I will present to you later on some rules no on assigning oxidation states, which I got from a certain source. Okay, so notice that hydrogen, since it is in elemental form, has an oxidation state of 0. Now, hydrogen in the process loses 1 electron, but there are 2 atoms of hydrogen, so 2 times 1. So, we have 2 electrons lost in the process. Okay, so from 0, it became positive 1. So, since there are 2 electrons lost, we need to multiply this with 2. Okay, now, for fluorine, initially it has an oxidation state of 0. It became negative 1 because it gained 1 electron. Again, there are two atoms of fluorine, so there are actually 2 electrons no gained by the fluorine. So the number of electrons lost and gained, 2 and 2 are now balanced. So final equation would be 1 mole of hydrogen plus 1 mole of fluorine is equal to 2 moles of hydrogen fluoride. Next, we have the reaction between ferric chloride, hydrogen sulfide, forming ferrous chloride plus the elements sulfur and hydrogen chloride. So again, we need to identify the oxidation states. Okay. So sulfur, iron rather, is positive 3. Chlorine is negative 1. So if you remember your formula writing, you know that this formula, ferric chloride, is simply arrived at using the crisscross method. Here, iron is actually positive 3 and chlorine or chloride is negative 1. That's why we affix those oxidation states here. Okay? Sulfur is negative 2, hydrogen is positive 1. Okay? Notice that you have charges, positive charges equal to the negative charges, such that the net charge of the compound is 0. So for iron, you have positive 3, and then chloride, you have negative 1 times 3, that's negative 3. Negative 3 plus positive 3 is 0. Similarly, for sulfide, we have negative 2. Hydrogen is positive 1 times 2, that's positive 2, plus negative 2, that's 0. Okay, so you do the same thing to all the elements. Okay, and then you look at the charges which increased or decreased. Okay, so in our example, sulfur increased rather from negative 2 to 0. So you know that 2 electrons were lost. You multiply this by 1 because the subscript is 1, so we actually have 2 electrons lost during the reaction. On the other hand, iron from positive 3 is reduced to positive 2. So 1 electron is gained. Notice that the number of electrons gained and the number of electrons lost are not balanced. So what do we do to make the equation balanced? We multiply this by 2. That's why there is a red number 2 here to indicate that that is the multiplicand ng multiplier 2 here, so that the number of electrons lost and gained now will be the same. So you have 2 electrons gained and 2 electrons lost. And then the rest, you balance by inspection. Okay? So we have 2 moles of ferric chloride. So we must affix 2 here. Okay? And then you count the number of ions. So you have 2 iron, 2 iron. What about chlorine? So there are 2 times 3, 6. You only have 2 times 2, 4. So you need to affix 2 here, so that you will have 6 chlorine molecules or atoms rather in the right side of the equation. What about sulfur? You have 1 sulfur, you have 1 sulfur here. Hydrogen, you have 2 times 1, so you have 2. And then you have 2 times 1, you have 2. And therefore, everything has been balanced. Now, so I have here 10 rules for assigning oxidation number. So the first one is that The convention is that the cation. So the cation is the one which is written first, no? Written first in the formula, followed by the anion. So recall your formula writing, no? Okay. So for example, in sodium hydride, hydrogen is negative. But in HCl, in most compounds, hydrogen is positive. Why? Because sodium is more electropositive, and therefore hydrogen is written second and would take the -1 oxidation state. Now the oxidation number of a free element is always 0, like what we had earlier, no? Fluorine and hydrogen are both 0. So for example, helium and nitrogen have oxidation numbers of 0. The next, oxidation number of a monoatomic ion equals the charge of the ions. For example, the oxidation number of sodium is +1, sodium being an element of group 1. Okay? The oxidation number of nitrogen is -3, nitrogen being a member of group 5. Okay? So it needs 3 electrons for it to be able to follow the octet rule. The usual oxidation number of hydrogen is +1, as I mentioned earlier, but in some cases it's -1. Now, the oxidation number of oxygen in most compounds is usually -2, except for oxygen fluoride, because fluorine is more electronegative, than oxygen, and therefore fluorine is written on the right side. So fluorine is -1, therefore oxygen here is +2. And barium oxide, due to the structure of the peroxide, where oxygen is assigned an oxidation state of -1, because barium is +2. Okay, so remember that the oxidation number of group 1 element, so the alkali metals, are +1. The alkaline earth metals is +2. The oxidation number of group 7 is -1, like fluorine, chlorine, except when that element is combined with one having a higher electronegativity. For example, in hydrogen chloride, chlorine has a charge or oxidation state of -1, but the oxidation number of chlorine in HOCl is +1, because oxygen, why? Because oxygen is more electronegative than chlorine. The sum of oxidation numbers of all atoms in a neutral compound is 0, whereas the sum of oxidation numbers in a polyatomic ion is equal to the charge of the ion. For example, sulfate has an oxidation state of -2. Okay. So this is taken from the article of Dr. Helmenstein. So let us try to apply the rules. For example, we have hydrogen sulfate, which is a neutral atom. So we would expect the total charge to be 0. Okay, so we would assign hydrogen first because it's more electropositive. So hydrogen is +1. But there are 2 atoms. So you have +1 times 2, that's +2. And the sulfate ion has a charge of -2. Okay, so what happens? So you have +2, and then the sulfate ion has a charge of -2, and oxygen is -2, so -2 times 4, that's -8. For this to have a charge of -2, sulfur must be +6. Here, the overall charge can be checked, and this is equal to 0. So we have another example, potassium permanganate. Okay, so again, we assign the more electropositive element, which is potassium, belonging to group 1. So potassium is +1. Again, you can check the values from your valence table. Permanganate ion has a charge of -1. Okay, so oxygen is almost always -2. So -2 times 4, that's -8. And therefore, what happens? For this to have a charge of -1, since oxygen is -8, manganese must be +7. Checking for the overall charge, potassium is +1, manganese is +7, and oxygen is -8. So overall charge is 0. So let's have this exercise, no? So you have, so nitrogen dioxide. So oxygen is always negative 2 if it's the more electronegative element. So negative 2 times 2 is negative 4. So nitrogen here must be positive 4. What about the nitrate ion? So all of this has a charge of negative 1, as opposed to this, which is a compound. No, this one is a polyatomic ion. So this has a charge of negative 1. Again, oxygen has a charge of negative 2. Negative 2 times 3 is negative 6. So negative 6 plus the charge of nitrogen must be negative 1. Simple algebra would yield nitrogen having a charge or oxidation number of positive 5. What about calcium dichromate? So again, we assign the more electropositive element. Calcium being an alkali metal has a charge of positive 2. Again, oxygen has a charge of negative 2. So negative 2 times 7, that's negative 14. So you have 2 plus the oxidation state of chromium plus the oxidation state of oxygen. So the sum must be 0. Simple algebra would give you 14 minus 12, that's 16. But take note that there are 2 atoms of chromium, so we divide that by 2. So 12 divided by 2, 6. And therefore, we know that the final charge of chromium is positive 6. Okay, so we have the bisulfate ion. So this whole thing has a charge of negative 1. So again, hydrogen being the more electropositive element is assigned an oxidation state of positive 1. So oxygen is negative 2 times 4, that's negative 8. So sulfur is unknown. Sulfur is unknown. And thus, simple algebra would give us oxidation state of sulfur being equal to 8, which is the charge of oxygen, minus 1, which is the charge of hydrogen, minus 1, which is the total charge. And therefore, sulfur is positive 6. So that if you add this, there should be a sum of negative 1. So positive 1 plus positive 6, that's positive 7. Negative 2 times 4 is negative 8. Negative 8 plus 7 gives us negative 1. Okay? So this one, hydrogen is the more electronegative element, and thus is assigned a negative 1 oxidation state. Okay? So I hope that is clear to you. So let me recap the steps. If you are given a reaction, no, where you are asked to balance using the redox, you identify first the oxidation state of each element, and then determine the number of electrons lost or gained in the process by checking the charges or the oxidation state. If there is an increase in the oxidation state, therefore electrons are lost. If there is a decrease, that would mean electrons are gained. And in the end, the number of electrons lost must be equal to the numbers of electrons gained. So normally you do the crisscross method. No? The coefficient of the substance, for example, which loses an electron must be equal to the number of electrons gained by the other substance. So as an assignment, I would like to give these 2 equations to you and balance this by redox. So the first thing that you need to do is to assign oxidation states to each element and check which element has an increase in the oxidation number or which one has a decrease in the oxidation state. Okay, and after that, you need to balance the number of electrons lost or gained. I was not able anymore to write the physical state because there are so many entries. Otherwise, the space will not be enough. Okay, and I will be compelled to use a smaller font for this one. So I opted not to write the physical state anymore, which I did man in the second equation. So gas Aqueous is in solution with water, no? Water being the solvent. You have aqueous, liquid, gas, and then aqueous. Okay, so that's all for now. I hope to see you next meeting. So if you have questions still, you may direct your questions to me using the Google Classroom or the chat group. Thank you and see you next meeting.